Okay, ¿no? Yeah.
So you do your microphone?
No, so I actually have.
Okay.
Couple of minutes late.
Check. 1, 2, check.
So when it's a Friday, I think it's okay to start a second.
All right, morning everybody. And with the usual story, turn off your laptops, your Thank you. Okay, folks, the usual story, shut down your laptops, your phones, the lot, once you're done with the attendance. It's a very sparse crowd today. There was an announcement that today was a class, so we should have had most of you in class today. I mean, Fridays are mandatory. They're not optional. So it's a bit disappointing that most of you are not here. Regardless, we're going to have this lecture, and the materials of this lecture will turn up in the quiz, which means that if those who are not here are going to have to watch the video. And you get your, attendance marked. Yes. Pardon me? It's not up. Doesn't matter. It's a Friday, right? Okay. All right. Here's where we were. Morning. We've seen so far that the problem of training a neural network is one of empirical risk minimization. We are given a collection of training points, each one comprising an input and the target output. And we define a loss, which is the average divergence between the actual output of the network and the desired output of the network over the entire training set. And we learn the network parameters to minimize this loss. And since the x's are given, this loss is a function of only the network parameters and everything else. So this is a problem of function minimization. So we're going to take a quick look at function minimization. Firstly, before we begin, does anybody know what a derivative really means? So how do we define a derivative?
Slope.
A slope. Rate of change, yeah. All of these are good definitions, but the correct definition is if I have some function, f of x, then at any given x, if you perturb the x by a small amount delta x, this is going to result, if you go from x to delta x, this is going to result in a small change in y. And the derivative at x is defined as the multiplicative term that multiplies the small perturbation in x to obtain the corresponding perturbation in y. Now, this is the only correct definition. This kind of applies globally. But if you have a function which is a scalar, where y is a scalar and x is a scalar, then we can write it like so. alpha is going to be a scalar, because if x and y are both scalars, delta y and delta x are also scalars. You can divide a scalar by a scalar. And so we like to write the derivative as dy over dx. But a more reasonable representation is f prime of x. Why would that be? Anyone? Why would f prime of x be more appropriate than dy over dx? Yeah. If you're not working with scalars, it's a little weird to have that ratio. But then more importantly, it indicates the fact that this is a function of x. At a different location in x, that derivative is going to be entirely different. So we like to have our representation to be very explicit, to indicate the fact that this multiplicative term is a function of x. And so now we get this property. This is alpha, this derivative is just a ratio. So if a small increment in x results in an increment in y, what will the sign of the derivative be? Can we hear that loud? Right, thank you. So in that case, this guy is going to be, for an increasing function, that's the slope is always going to be positive. On the other hand, if a small increment in x results in a decrement of y, what is the sign of the derivative? Negative, right? Thank you. And now if you have a function which is kind of increasing and then starts decreasing, and it's continuous and differentiable, then your slope is going to be positive for a while as the function's increasing, and then suddenly the function stops changing, and then the slope is going to become negative. And because everything is continuous, it means that for the briefest moment, right at the very peak, the derivative is going to be 0, right? So those points where the function goes from being increasing to decreasing, that is a local minimum, local maximum. That's called a turning point. Similarly, if the function goes from decreasing to increasing, that is also a turning point. And at turning points, the derivative of the function is going to be 0. It's going to be locally flat. Now, if I have this notation of dy over dx, works when x and y are scalars. But then let's think of a multivariate function where x is a vector and y is still a scalar. So in this case, the function is going to have a shape of this kind. They maybe, if the input is two-dimensional, you could have a function that looks like a bowl. But when the input is a vector, how do we define the derivative? We're going to still use the same notation. Once again, at any x, I can take a small incremental step delta x. So we have y equals f of x again. But f of x, I'm going to assume, is a column vector which has components x1 through xn. Then once again, the derivative is defined as the multiplicative term that multiplies a small increment in x that gives you the corresponding increment in y. So alpha delta y is going to be alpha times delta x. But what is delta x? What kind of a variable is delta x? Is it a scalar? Yes, no?
No.
X is a column vector, right? So what is delta x going to be? Also a column vector, right? So delta x is going to have the form delta x1 through delta xn. What is delta y? Scalar, right? So given this, what is delta y? Thank you. What is alpha going to look like? Delta x is a column vector. Delta y is a scalar. So what does alpha look like?
Row vector.
Alpha is going to be a row vector. So in this case, alpha is going to have this form, alpha 1 through alpha n. And I can write delta y equals alpha 1 delta x1 plus alpha 2 delta x2, and so on. So here's the thing. When your argument is a column vector, the derivative is going to be a row vector. If your argument were a row vector, what would the derivative be? column vector, and it would have to right multiply. Is that making sense to you guys? Right? And so one more thing. If I'm at any point x, is there only one direction in which I can perturb x? Yes or no? No. Right? I can actually take a step in any direction from any point. So one particular direction would be one where I only change this guy, and the rest of the steps are 0. This is also an increment. In this case, what is the change going to be? What is delta y going to be from the formula? Yes, in this case, this is just going to be alpha 1 delta x1. So this is what is called a partial derivative of y with respect to x1. It is how much y changes when all the other x's are fixed and only x1 is perturbed. And so using this notation, your derivative, your increment delta y is going to be the partial derivative of y with respect to x1 times delta x1 plus the partial derivative of y with respect to x2 times delta x2, and so on. Is this clear to everybody? Yeah, okay. And so I can write it like so. I'm going to represent my derivative using this inverted triangle called a nabla. This is a derivative of y with respect to x. The subscript x shows you that it's the derivative. The derivative is with respect to x. And this derivative is going to be, what's it going to be? What kind of a structure? If x is a column vector, what is this derivative again? Row. It's a row vector. And the entries are the partial derivatives of y with respect to x. Now, how many of you have heard the term gradient? Most of you. Now, the gradient is a vector that... Oh. So the gradient is a vector that's actually, that lives in the same space as the original data itself. So then if the data are column vectors, the gradient must also be a column vector. It's defined as the transpose of the derivative. Right? It's number one. So far so good. I have delta y equals the derivative times delta x, or alternately the inner product between the gradient and delta x. So we know how the gradient is defined arithmetically, but what does it really mean? What is the gradient? Anybody know?
Direction of the steepest increment.
That is the direction of the steepest increment. And the reason for that is simple. If I have a function at any point x, the gradient is a vector. It's a vector of partial derivatives, right? And my delta x can be in any direction. This could be my delta x, or this could be my delta x. It doesn't really matter. And if you'll observe, delta y was defined as the gradient times delta x. This is the inner product of the gradient and delta x. What do we know about the inner product of two vectors? The inner product of two vectors is defined here, as we all know, as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. So if I'm taking a fixed size step, then there are many directions in which I can take the fixed size step. In which direction must the fixed size step be for this inner product to be maximum? In the same direction as the gradient, right? So in other words, if you take a step in the same direction as the gradient, that's when the inner product is going to be maximum, right? And so the gradient is the direction of the maximum fastest change of the function. Right, everybody? Right, okay. And so dy or df is going to be the inner product between the gradient and dx. And this is, and so the gradient is the direction in which the function changes fastest. And the magnitude of the gradient tells you how fast the function changes. It has two components, the direction and the rate of change itself, the magnitude itself, right? And so when I have a function of this kind, at any location x, the gradient is the direction in which the function increases fastest. If I'm looking for the direction in which the function decreases fastest, what is that? Are you taking notes? You there? Are you taking notes?
No.
Please shut your laptop. Yes. Okay. So what is the direction in which the gradient decreases fastest? I mean, the function decreases fastest. It's going to be the exact opposite direction, right? So moving in this direction increases the function fastest, and moving in this direction is going to decrease the function fastest, right? And if you have a turning point, that's where, at that point, regardless of the direction in which you're moving, the function does not change for really tiny movements. And so the gradient at the turning points are going to be 0, right? Now, there's another property of gradients that we often use, that if I take a level set of a function, does anybody know what a level set is? So, right, so if I think of a two-dimensional function over 2 dimensions, it's going to be some surface, maybe like this. I can slice it at a particular height. And if I slice it at a particular height, what am I going to see? I'm going to just see a bunch of edges, right? Those edges represent the level set. At that, it represents a locus where the function value is constant. And the gradient is always going to be orthogonal to every level set of the function. Everyone with me? Yeah, okay. There's another property of multivariate functions which characterizes how it changes, called the Hessian. The Hessian is a matrix where the ijth entry of the matrix is the derivative of the function with respect to xi and xj, the second derivative with respect to xi and xj. This is just a definition. There's more about Hessians in the slides. Please take a look. So here's your first part. Okay. For the first question, do we have people on Zoom? Because there must be people on Zoom, considering there's nobody in class. So the first question, there are three options. All three. I need someone on Zoom to tell me they're right. Is the first option correct or wrong? Somebody on Zoom.
I think it's correct, right?
Yes.
Thank you. What about the second one?
Also correct.
And the third?
Not sure.
Okay. Does somebody in this room want to answer? Is the third option correct?
It's correct.
The gradient is the transpose of the derivative, right? I cheated over there. Okay. What about the second question? What's the answer, guys?
1 times n.
Thank you, right? So you get the idea. So let's move on. We're talking about the problem of optimization. And the problem of optimization is this. You're given a function which increases and decreases. And optimizing the function often deals with finding either the maximum value or the minimum value of the function. So there are two aspects to it: finding the value of the function itself and finding the location at which this maximum or minimum is achieved. So in our case, since we are trying to minimize losses, we're going to be speaking of minimum. And so here is the problem we have, trying to find the minimum of a function. And how did we solve this in school? So guys, can you shut your laptops if please, okay. You got there after the poll, right? There was a poll here. Why did I get a poll? I'll leave it here, sorry. This took me by surprise. I was here, just bounced, okay. That's okay. How do we compute the minimum of a function? Anybody remember? Set the derivative equal to 0. Is that sufficient? No. What else must we check? The second derivative of the function, right? So we are trying to check that f prime of x equals 0. And specifically, if you're looking for the minimum, you want the second derivative to be positive. Why would that be, right? Let's take a look. Now, if I have a function of this kind, then over here, if I look at where at a maximum, oh wow, look at the negation, right? So if I have a maximum, the slope here is going to be positive, becomes 0 here, and then becomes negative out here. So if I were to plot the slope with this point here, to the left of this point, the slope is going to be positive. To the right of the point, the slope is going to be negative, right? What is the slope of the slope at this point? It's going from positive to negative, right? So what is the sign of the second derivative? Negative, which is why at maxima, the second derivative is going to be negative, right? Similarly, if I have a minimum, the slope is initially negative, then it becomes positive. So if I plot the slope, it's going to go from negative to positive, which means that the second derivative is going to be positive, right? So that's why the check we run is all the maxima and minima are both turning points, and the derivative is going to be 0 in both cases. The second derivative will be negative for maxima and positive for minima. And so in school, you learned that when you want to solve for the minimum of a function, you're going to equate the derivative to 0, and then you're going to find whether the second derivative is positive or not. If it is positive, it's a minimum, otherwise it's a maximum. So this is easy enough. But then, derivatives are ugly things. So derivatives can go to 0 in all kinds of situations. For example, if I have a function of this kind, this is an inflection point. So at a maximum, that's a turning point. The function went from being increasing to turning around and start decreasing. At a minimum, the function went from decreasing, and then it turned around and went back to being increasing, which is why the derivatives since the slope has changed from positive to negative, it became 0 at the turning point. But then here is an inflection point where the function was decreasing and then briefly paused and then continued decreasing. So in this case, what does the derivative look like? If I plot it, here's what you're going to see. I have a function that's decreasing and then sort of slowed down and then continued decreasing. The derivative is negative here, it's negative here, and here it's 0. So what will the derivative plot look like? Anybody? Yes. What's on the slides, right? The derivative is going to be negative, but it's going to become less and less negative as I approach this inflection point. At the inflection point, it is 0. But then it goes back to being negative. So unlike the previous case where the derivative crossed over at the axis, here it does not. So what would the second derivative be over here? It's going to be 0. At the inflection point, the second derivative is going to be 0. So it's not sufficient to just check for the second derivative in most cases. Functions can do horrible things, right? And it's a little, and when you begin looking at functions of multiple variables, it gets even more hideous. Because when I'm looking at a turning point for a function of multiple variables, when I have a minimum, then it doesn't matter which direction I'm approaching the minimum from. Initially, the function will decrease and the function will increase. If I approach the minimum from a different direction, the same thing happens. The function will initially decrease and then begin increasing. But then I can have other kinds of functions of this sort. What happened? How did I lose my chalk? Yeah. So where I could have behavior of this kind, where the function maybe does, so the function is like a bowl, I mean, it's like a saddle. So then what happens? This location is strange. If I approach in this direction, that is a minimum. If I approach in this direction, that is a maximum, right? And so these are strange locations where, depending on the direction from which you approach the function, from the location, the behavior of the function changes. Those are not minima, and those are problematic. So when I have functions of multiple variables, you can still, or the optima are still turning points, which means regardless of the direction in which I approach it from, it's going to be, the function will begin changing its slope. And so at the turning point itself, the gradient is going to be 0. And so if you want to find out where the function, the location of a minimum, the least you can do is to find the location at which the gradient is 0, but that's not sufficient. You want to also, as we saw, as in the case of the scalar, you want to find this, how the second derivative behaves. And the second derivative captures is captured by the Hessian. Now, what is the Hessian? We just showed you the Hessian matrix, but then the Hessian matrix has an interesting property. The eigenvectors of the Hessian matrix capture the main directions of change. Here, in this case, one direction is like so, the other direction is like so. They're orthogonal to one another. And the eigenvalue of the Hessian gives you the second derivative in that case, in that direction. And so in this function, what are the eigenvalues of the Hessian going to be at this location? The signs. Can anybody tell me? Yeah. One is positive, right? For this guy, for this direction, the eigenvalue is going to be positive. For this direction, the eigenvalue is going to be negative. And so if you want to actually check if a function is an actual minimum, you'd have to check the Hessian. And you'd have to ensure that every single eigenvalue is, what will it have to be? Positive. If it's not, then it's not a minimum. It's likely a saddle point. It makes sense to everybody? Right, okay. So now there's an example on the slides where you actually work through this kind of an optimization, where you compute the gradient, you equate it to 0, you find a solution, then you check the Hessian at that point and the eigenvalues of the Hessian to ensure that it is indeed a minimum or a maximum. But then more generally, you're going to get some very nasty functions of this kind. And for functions of this kind, you can't really just compute the derivative and equate it to 0 and figure that you've gotten to wherever you want to get to. So in these situations, we need to have iterative solutions. We begin with a guess for the optimal x, the x at which the function is minimum. So you start off at some point, maybe x0, and then you will look around and check if this indeed is a minimum. So what would the check be? You can just check if the slope is 0. If it's not, it means that there's some other point you must move. And so you take a step. Then you repeat the test. And you keep doing this until you arrive at a point where the function is flat, or any further steps don't change the function. And of course, you've got to figure out which direction to step in and how big the step must be. These are issues. But this is the iterative solution to finding the minimum. Now, let's consider specifically the direction in which you must take the step. So let's say I have a function of this kind. I start off with an initial guess at some point. And then I find that the slope at this point, I'm trying to find a minimum, right? And so at this initial guess, I find that the slope is positive. If the slope is positive, will taking a step forward, incrementing x, increase the function or decrease it? Increase it, right? So which direction must I take the step in? To, I must go backwards. On the other hand, if the slope, if I take the step, if the slope is negative, then if I take a simple step forward, will the function increase or decrease? Decrease. So what is the correct direction to move in? Forward, right? So in the scalar case, here is a simple, trivial solution for how you can begin approaching a minimum. At the current solution, at the current guess, you check the derivative. If the derivative is 0, then it's maybe a minimum. Otherwise, you can check the sign of the derivative. If the sign of the derivative is positive, you want to take a step back. If the sign of the derivative is negative, you want to take a step forward. I can write this without an if clause in a single step in this manner. I can just say that the new estimate is going to be the old estimate minus the sign of the derivative times the step. Why minus? This way, if the sign of the derivative is negative, minus and minus become positive, you're going to go forward. Whereas if the sign of the derivative is positive, then you end up taking the change is negative. You go backwards. And so this would be a very simple rule for ensuring that you're always headed in the direction where the function is decreasing. And of course, I can now I can make one additional assumption. We like nicely behaved functions, and a specific kind of a nicely behaved function is a function that looks like a bowl. So if I have a function that looks like a bowl, and I'm doing this incremental stepwise progression towards the minimum. Now out here, the slope is very large. So at this point, so if your current estimate is here, do you want to take a large step or a small step? A large step. So on the other hand, if you're out here, what kind of a step do you want to take? A small step. So in other words, wherever the magnitude of the slope is large, you want to take a large step. Wherever the magnitude of the slope is small, you want to take a small step, if you want to be careful. So I can factor that in, and I can just say that the steps which is not only proportional to the negative of the sign of the derivative, but to the negative of the derivative itself. So this ensures that not only are you going in the correct direction, the step size depends on the slope. This makes sense to everybody, right? And so this is the famous gradient descent algorithm. Xk plus 1 is xk minus some multiplicative factor called the step size times the slope. So but this is for a scalar. So we're not really doing gradient descent. This is more like a derivative descent. For multivariate functions, it actually becomes something slightly different. This pole should get you there. This is a repeat, right? But there's a reason I'm repeating this poll. Okay. Which of the statements are true?
A and B.
Mm-hmm. A and B, right? So this is now the derivative. So now if I am trying to optimize a multivariate function and I'm at some current location and I find that this is not the minimum, which is the most promising direction in which I must modify my estimate? I must go in the direction where the function decreases fastest, right? What would that be? The opposite of the derivative, of the gradient. And so here's what we will do. The gradient is the direction in which the function increases fastest. The negative of the gradient in which is the direction in which it decreases fastest. And so our update rule is going to be this. If I want to decrease the function, minimize the function, I'm going to take a step against the gradient. If I want to maximize the function, I'm going to take a step in the direction of the gradient. So since we're generally speaking of minimization, this is the rule that's going to be of interest to us. And this is the gradient descent algorithm. Now, why gradient descent? Because you're always taking a step against the gradient. Make sense to everyone? Okay. And so the gradient descent algorithm takes incremental steps against the gradient. When do we stop taking steps? When the gradient becomes 0. But here's a surprising fact. Checking for when the gradient or the slope becomes 0 is probably not the best thing you can do. So a better thing to do is to actually check the value of the function itself. And if additional steps are not changing the value of the function very much, then you're done, you can stop. So here's the overall gradient descent algorithm. You start off at some initial point x0. You're trying to minimize the function f of x. Then at each point, you take a step, xk plus 1 equals xk minus some multiplicative term times the derivative transpose. Why have I written the derivative transpose?
Gradient.
That's the gradient. The derivative itself is a row vector, right? So here's a general property that I want you guys to remember. If I have y equals f of x, if x is a scalar, the derivative is going to be a scalar. If x is a column vector, what will the derivative be? If x is a matrix of n cross m, what do you think the derivative is going to be? It's going to be the transpose. It's going to be an m cross n matrix. This is a general property. The derivative is always going to be the same shape as the transpose of the argument. When we speak of the gradient is the transpose of the derivative. It's going to be the same shape as the argument itself, right? And so this is what we do, and we keep taking these steps until the function no longer changes. Now, how well does this behave? If you have bowl-shaped functions of the kind on the top, then gradient descent will cleanly converge to the solution. On the other hand, if you have uglier functions like the one to the left, then gradient descent can do all kinds of things. It can get stuck on a saddle point or one of those local minima inflection points because the function has sort of slowed down over there. Or it can go into local minima. There are other points where the function is lower still, but then you just got a local value. These things can happen. And in particular, if it's a local minimum, then so long as you start in the vicinity of it, you're going to end up over here. But these inflection points are strange. If you started to the left of the inflection point, you're not going to go there. If you start to the right, you're going to go there and get stuck. So gradient descent can have unpredictable behavior. Okay, anybody want to answer this question? Here? See? Exactly opposite the direction of the gradient at x0, right? Easy. So that was a detour into gradient descent. But what was it we were really trying to do? We were trying to figure out how to optimize a neural network. So let's go back to our original problem. You're given a training set of input-output pairs. We defined a loss function, which was the average divergence across the training set. And this loss function was only a function of the parameters w. And we wanted to minimize this with respect to w. So can we apply gradient descent here? Yes, no? Can I hear a no or a yes? Yes. Thank you, right? And how would you do this? Again, Anyone?
Gradient descent.
So you would start off exactly this as before. You're going to start off with an initial guess for W. And then at each point, you're going to compute the gradient of the loss with respect to W. And then you're going to take a step against the gradient. But then it's something that you want to, there's a little bit of intuition here that I would like you to carry with you. The gradient is a vector of partial derivatives with respect to the various parameters. At the end of the day, what are we really doing? You're looking at d loss by dwi, which is wi is the individual, these are the partial derivatives, right? Wi's are the individual parameters of the network, and we're always asking ourselves, does increasing this parameter increase or decrease the loss? That's all. It comes down to this. You look at each parameter and say, will increasing this parameter increase or decrease the loss? And if it turns out that increasing the parameter will decrease the loss, you're going to increase it. If it turns out that decreasing the parameter is going to decrease the loss, you're going to decrease it. That's at the core of it, that's all gradient descent is about. We write a lot of very complicated math, but the intuition is you're just checking the derivatives to see whether, increasing the parameter will decrease the loss or not. And depending on what happens, you're going to modify the parameter. So anyway, so this is basically what we want to do. But before we go about doing this, we have to set up the problem. And here's the problem setup. We have a bunch of input-output pairs, where each training instance has an input X and a corresponding output. I've called it D because D is the desired output. This is the actual function G that I showed in the previous class, which is distinct from the actual output of the network. So each training instance is an input X and the desired output of the network, D. We have a collection of those. The loss is the average divergence between the actual output of the network, f of x, comma, semicolon w, and the desired output d. And this loss is what we want to minimize. Now, just stating it in this manner is not really, enough. There are many things we must specify. What are these input-output pairs? What is this function f? What is this network? What is this divergence? We have to define that too, right? And without defining all of these, we cannot really perform this optimization. And so let's start off by first looking at what is this function f. This function f for us is a neural network. Specifically, we're going to assume for now that it's a multi-layer perceptron, but the concept generalizes to any kind of neural network. And the thing is, the key point is that it's a directed network where you have an input and the input flows through the network through a bunch of hidden layers and eventually arrives at an output. So we're going to assume a layered network. As we saw earlier, every network is layered. But what I mean by saying a layered network of this kind is that all the output neurons are the same depth. I mean, I can always draw a network where different output neurons are different depths, but those are ugly for ugly networks. So we are going to assume that all the output neurons are the same depth. The inputs are really just inputs. There is no neuron. There are no neurons at the inputs. But from convention calls the inputs the input layer. So we're going to call that the input layer. We're going to call the output neurons the output layer, and everything in between is called hidden neurons. These are hidden layers. There's nothing hidden about them. You can inspect them. The reason we are calling them hidden layers is that the individual outputs are not specified. We don't really care. Like in the case of the XOR, you're not really worried about what the intermediate neurons generate, so long as the final output neuron correctly computes the XOR. And so that's the structure. What about the individual neurons themselves? We're going to assume the individual neurons have the structure of the perceptron we saw earlier in class, where you first compute an affine function of the inputs, and then you put this affine value z through an activation, where the activation could be a sigmoid or a ReLU or anything else. Now, more generally, that neuron could be any differentiable function of the inputs with some parameters. And so in some cases, we will also use this more generic case of a neuron. But this is the most standard neuron. Again, our neural networks are complicated networks of simple units. And so this unit is about as simple as you can get. Yes, Virginia.
A terminology question. Is a multi-layer perceptron equivalent to a feed-forward network or a sequential network?
A multi-layer perceptron is a feed-forward network. So in this case, things are being processed sequentially, right? And so we are going to assume this kind of perceptron unless otherwise specified. And the parameters of the individual perceptrons are the weights and the biases of the perceptron. And so the overall network is going to be a collection of these, a network of these perceptrons, and the parameters are the set of weights and biases for all the perceptrons in the network. And what about the individual perceptrons themselves? They can have different kinds of activations. The most common activations are the sigmoid, which goes smoothly from 0 to 1, as we saw in the last class. The tan H is simply a shifted sigmoid, which is centered at 0. So instead of going from 0 to 1, it goes from -1 to 1. We've seen the ReLU, which is 0 for negative inputs, and the same as the input itself for positive inputs, and the smoother version of the ReLU, which is called the soft plus, shown by the blue curve. Now, in each case, we need to also know what the derivative of the activation function is going to be, and it's easy enough to figure out what the derivative is via inspection. So use this. If I have a function of this kind, clearly the derivative is initially 0. It's also finally 0. Then in between, the derivative is going up, and then it's coming back down. And for the sigmoid, this peak value is going to be 0.25. For the tan H, the peak value is going to be 1. Now, if I have an activation function of this kind, what will the derivative look like? Anyone? The slope here, what does the slope look like? 0. And what happens here? So that's your derivative, right? And for the soft plus, which looks like so, what do you think the derivative is going to look like? It's going to be, the derivative will be the sigmoid, right? So I have the formula, but you can actually sort of look at the activation function and get an idea for how the derivative behaves. You can also have these things that we call vector activations. Now, in all of these activation functions that we've looked at so far, the activation function takes in a single input and generates a single output. So you had this affine value z going into whatever activation, and it generated an affine value y, the output of the activation y. So if the layer had many neurons, each of them had its own z value, right? Z1, Z2, Z3. And each of them was operated upon individually by the corresponding activation, and you got a bunch of outputs y. But then there's a different kind of operation where I can just say that the set of z's goes in. Please don't travel. The set of z's goes in, which is z1, z2, z3, and a set of y's comes out. What is the key distinction between these two different kinds of activations? The key difference here is that if I modify z1, only y1 is going to change. The rest of them will not change. Whereas in something of this kind, if I modify z1, in the most generic case, you're going to have to assume that every one of these outputs changes. So this is why I'm calling it a vector activation. A vector goes in, a vector of x's goes in over here, a vector of y's comes out. And perturbing any input can perturb all of the outputs. So the most common of these vector activations is the so-called softmax. The softmax has this property that, again, a bunch of z's goes in, z1 through zn, and a bunch of y's come out, y1 through yn. But the y's are related to z's in this manner. yi equals e raised to zi divided by summation over j e raised to zj. So you're exponentiating each of these z's, then you're normalizing them to sum to 1. So the set of outputs are always going to be non-negative, and they're going to sum to 1. So what does that look like? You have a bunch of numbers that are always non-negative and sum to 1.
Probability.
That looks like probability. So this computes something that looks a lot like a probability distribution. But then look at this. If I increase z1, what will happen to y1? Will that increase or decrease?
Decrease.
Guys, if I increase z1, will y1 increase or decrease?
Decrease.
Increase. Does everybody agree? Right? But if I increase z1, what happens to the other y's? Will they increase? Yes or no? Can I hear a collective no? Okay, louder please.
No.
Thank you. Including you guys at the back. The next time I'll expect you to yell as well. So why will the rest of them decrease? Because they are normalized. If something goes up, something else has to go down because they all sum to 1. So is the derivative of y1 with respect to z1 positive or negative?
Positive.
Can I hear a loud positive? Okay, and what is the derivative of y1 with respect to zn? Negative, because if I increase zn, then yn is going to increase, which means y1 is going to go down. Right? So every z influences every y. Make sense, everyone? Right? So that's a typical, we're going to see more of the software later. And so in a typical layered network, I can just think of each layer of perceptrons as just being a vector activation. That's a perfectly acceptable interpretation. But then, if I think of the layer, every layer is a vector activation. For layers which just have these, which are just compositions of little maybe ReLUs applied to each zi's, it just means that the cross derivatives are 0. Modifying z1 only modifies y1. Whereas for layers where you have activations of this kind, the cross derivatives are going to be non-zero. Modifying z1 is going to modify y2 as well. So we've specified f. There were many things to specify. The function f, and the function f is a multilayer perceptron, where the individual perceptrons first computed an affine function of the inputs, and then passed it through an activation. Then, the entire network itself was a network of such perceptrons. What are these guys? The input-output pairs. Now, for this, we have to consider that there are 3 different things that going here that figure. One is the input itself. Aryan and Arihant, you guys want to go wash your faces?
Sorry, my nose is right.
No, he's falling asleep. Go ahead and wash your face. Yeah. Yes.
I have a question regarding the vector activation functions. Why are they necessary? Why are
We will see.
because, oh, okay.
Okay. So they're typically used in the output layer. When you're performing classification, let's say you're choosing between 100 classes. If you increase the probability of the first class, what happens to the probability of the second class? So at the output layer, you almost always have vector activations. That answer your question? Okay. So now there are 3 different things we want to specify. We want to specify the input x. We want to specify the desired output y. And then we also want to specify the actual output of the network y. And so any input-output pair has an x and a d, but implicit there is also a corresponding y, and all 3 have to be defined. X can be a vector. It's a vector of inputs. The desired output d is a vector. And then the actual output of the network is also a vector. So all 3 must be specified. And we'll have collections of these. So when I have many input-output pairs, each instance is going to be an input vector and a corresponding desired output vector. So what is the input? The input, now remember, we're dealing with numbers. So it must be a vector of numbers. And these are often very easily derived. So it could be a vector of pixel values, or it could be a vector of speech features derived from a speech signal, or it could be a vector of something else, like numeric vector-based representation of text. So even when you're dealing with text, eventually you're going to have to convert it to a numeric vector representation in order to feed it to the network. So that's the input. What about the output? Now, if the desired output is real valued, for example, if I'm computing a regression, then the output, and let's say I'm computing a scalar output, like I'm looking at a whole lot of numbers, and then I'm just predicting maybe the stock price for some stock tomorrow. It's a scalar. So in that case, the desired output is going to be a scalar, and clearly, your network is going to have just one output neuron, which is predicting this real value for the output. And even in the real case, you can have a real valued vector output. For example, if I'm predicting the entire stock market, then the neural network is going to have as many output neurons as the number of stocks you're considering. And you're going to get the output is going to be a real valued vector where each component corresponds to one of these outputs. So in the real valued case, it's very easy. Again, the number of output neurons, the number of outputs of the network must be the same as the number of as the dimensionality of the desired output of the network, or the number of elements in the desired output. Now, if I'm performing classification, like a binary classification, is this a cat or is this not a cat? Then anytime you present a training instance, you're going to give it maybe a picture of a cat and then the desired output is 1. Or you might give it a picture of a table and the desired output is 0. So we will need a binary representation of the output. And since there's only one output coming out, the neural network itself is simply also going to have just one neuron. And what kind of neuron will it be? Typically, we will here have a sigmoid activation for that one neuron. A sigmoid activation goes smoothly between 0 and 1. And the value that it produces can be viewed as the probability that the input is the desired class. So you give it a picture, it's fuzzy. The output says, what is the probability that this is the picture of a cat? Now, so we can think of this as P of y equals 1 given x. That's what the network computes. If I have a multi-class output, like I'm computing an output, the network must decide if the input is a cat, a dog, a camel, a hat, or a flower. So I've specified a number of different classes, and the network must choose from one of these. Now, cat is not really a number, so we must convert this thing to a numeric format first. So here's what we will do. We're going to use what is called a one-hot representation, and we will arrange all of our classes in some pre-specified order. So I might say that I'm going to arrange my 5 classes, cat, dog, camel, hat, and flower, in that order. And now, cat, dog, camel, hat, flower, right? Now, when I get a training instance which is a cat, then what I will do is that this is a 1 for a cat and 0 for all of these, because a cat is not a dog or a camel or a flower. So this will be my desired output, a 1 in the first component and 0 elsewhere. This is a one-hot representation for a cat. If my training instance is a camel, there's going to be 0 for cat and dog, 1 for a camel, 0 for a hat and a flower. And so this is a one-hot representation for camel, which is zeros everywhere, except in the index of the target class where the output is going to be, desired output is going to be 1, right? This is the desired output, and these are one-hot representations, or a one-hot vector. What about the network in this case? Here, we want the network to output, so the numeric representation of your classes is a one-hot vector, with as many components as the number of classes. So the output of the network 2 is going to have as many components as the number of classes. And specifically, we will have a softmax output. And the ideal output is that whenever the network sees a cat, it's going to give you a 1 in the cat position and 0 elsewhere. But is that what it will really do? It's never going to be so sure. So we will actually we'll try to compute a probability. We're going to use a softmax layer where the outputs sum to 1, and the output will be the probability of a cat. So this is going to be here this first element is going to be cat, dog, camel, hat, and flower, right? And when the network sees a picture of a cat, ideally this must be 1, 0, 0, 0, 0. But more realistically, it's going to compute a bunch of numbers which all sum to 1. And what these numbers represent are the probability that this input is a cat, the probability that it's a dog, and so on. And ideally, the network is really, really sure that it's a cat, and it assigns a probability of 1 to cat and 0 to everything else. But more generally, it will not. And that's why we use the softmax activation in this case, so that it can compute the probabilities of the classes. Once again, the ith component of the output is the posterior probability of the class given the input. Was there a question? Yeah.
What if picture has both cat and dog?
So that's what would you expect? Here you're making a unique classification. Once you begin looking at problems where you have multiple target outputs, then the network must be differently designed. It's a slightly more complex problem. It can be dealt with, but not exactly in this manner, right? Post on Piazza, I'll tell you how. And so, when I'm training, had we given a bunch of inputs and outputs, a typical problem statement, you'd be given a number of training data instances, e.g. images of digits, and information about which digit the image represents. If you're performing binary classification, you're just going to have, along with each training instance, is this the digit 2 or not? And that would be your training data. If you're performing multi-class classification, you're going to say that first digit is the number 5, the second one is the number 0, and so on. And then these are the training data that you would use. So this would be a binary class problem, where these are the data that you would be provided if you're trying to decide if the input is the digit 2. And here the network is going to have only one output, which outputs the probability of the digit 2. And here, when I'm actually trying to recognize the digit, then the network is going to have as many outputs as the number of digits that I'm trying to distinguish between. You would have a softmax output layer, and the training data are going to comprise images of the digits and the actual class, the number, which you will convert to a one-hot vector when you actually begin feeding it to the network. So we have specified the input-output pairs. We've specified the function f, but there's one more thing to specify, the divergence. Because without specifying the divergence, the whole thing is not specified. And so, again, we have requirements. The function f, the activations must be differentiable. They must be differentiable because you want to know how much a small perturbation of any given parameter will change the output of the network. But the divergence function must also be differentiable. We saw this in the last class. Because you want to be able to compute how much perturbing a specific parameter a little bit will change the overall loss. And if the divergence function is not differentiable, the result of perturbing any parameter cannot be computed. The outcome of perturbing this, how this modifies the final loss cannot be computed. So the divergence must be differentiable. So for the loss to be differentiable, divergence must be differentiable. This is key. Now here are some examples of divergence functions. If I'm making numeric predictions, then the most common divergence is simply the squared error. So why the squared error? You will see, it's very easy to see why. First, it's going to be half of the squared norm. So I have a desired output D. The network actually produces an output Y. So component-wise, I'm going to take the difference between the desired output and the network output. I'm going to square it. I'm going to sum these, and then I'm going to divide by 2. That factor of 1 by 2 is part of the so-called L2 loss in the context of neural networks. Now, why do we need this 1 over 2? This 1 over 2 is just to take care of derivatives. When I compute the derivative of this loss with respect to the output of the network. Now, again, we'll see this in the next class. When we compute when we want to learn the network parameters, here's what we would do. I'm going to have layers to my network. These are all my weights. And then eventually, I'm going to have the output layer. And then I'm going to compute my loss. So when I want to figure out how much changing this parameter changes this loss, here's how I'm going to do it. I'm going to determine how much changing this guy perturbs this one. How much changing this guy here changes this. How much changing this guy here changes this. And then I'm going to have to chain the whole thing, going from the output to the, all the way to the parameters I'm trying to adjust. So the very first thing I need to be able to compute is how much perturbing the output of the network will change the loss. So I need the loss to be differentiable with respect to the output of the network. And so here, we are looking at the derivative of the loss with respect to the yi's. And what is the derivative of the loss with respect to the yi's? If I define my loss as y minus d whole squared, what is the derivative of this with respect to y?
2 times.
2 times. So there's this factor 2, which we do not like. So if I define a half over here, this cancels out. You're left with y minus d. So now is this y minus d or is it d minus y? After all, I'm squaring it. It won't make a difference to the loss, right? So should it be y minus d or should it be d minus y?
Y minus d for the derivative.
Y minus d for the derivative to be positive. Can somebody, how can you be so sure? So if this ever confuses you, then here's a very simple way to look about it. Think about it. If y is less than d, so I have y, so y minus d. If y is less than d, right, then do you want to increase y or do you want to decrease y? You want to increase y, right? So when y is less than d, you want, what do you want the derivative to be?
Positive.
You want to say that increasing y decreases the loss, correct? So if y is less than d, do you want the derivative to be positive or negative?
Negative.
Negative. And is y minus d negative or positive? Remember, y is less than d. Is y minus d negative or positive? Negative. So does this have the correct sign?
Yes.
Okay, if y is greater than d, do you want to decrease y or increase y? Decrease y. So what do you want the sign of the derivative to be?
Positive.
Positive. Does this have the correct sign? So it's y minus d and not d minus y. You can sort of just look at it, then figure it out by thinking of how this influences the updates, right? That makes sense to everybody? And so that's why this derivative is y minus d. And observe that this is just the error between the output of the network and the desired output of the network. So that's why, and so why, this is why back in the day when they spoke of how to train a network, they call it error backpropagation. We'll talk about backpropagation in the next class, but the term that you're actually capturing, the derivative, is the error. And so that half over there makes sure that you're just getting the exact error, not a scaled version of the error. Now for a binary classifier, the output is either 1 or 0, right? The desired output is either 1 or 0, but then remember, for a binary classifier, how many classes do we actually have?
Professor, I have a question here.
Yeah.
Why are we differentiating by y? Why not by, we're differentiating by w, right?
So y is a function of w. So you're going to have to to differentiate with respect to w, first you'll need a derivative with respect to y.
Okay.
Right? Okay. So now, when I'm performing binary classification, how many classes do I really have? 2, right? So when I say that this is, if I give you a positive instance of a class, the 2 classes are yes class and no class. So if I give you a positive instance of the class, it's actually implicitly the vector 1, 0. If I give you a negative instance of the class, it's actually implicitly the vector 0, 1. And here, if the network only has one output, but it's actually generating 2 outputs, what are those? Yes.
Y and 1 minus 1.
It's generating 2 probabilities. It's generating the probability of the class, and it's generating the probability of not the class, which just happens to be 1 minus P of C. Right? That makes sense to everybody? And so here, we are going to define a KL divergence, which is minus, so this is D, the desired output, which is either 1 or 0. And the second component is going to be 1 minus D, which is the value assigned to the second class. This is going to be Y, which is the actual output of the network. And this is going to be 1 minus Y, which is the probability assigned to the implicit class, the negated class. And so the loss is going to be D times log of Y plus 1 minus D times log of 1 minus Y, the entire thing negated. So minus D log Y minus 1 minus D log 1 minus Y. That makes sense to everybody? This is the Kullback-Leibler divergence. And then now I can take D is going to be either 1 or 0. It's a desired output. If it's a picture of a cat, D is 1. If it's not a picture of a cat, 1 minus D is 1, right? So if you look at the derivative, if I take the derivative of the divergence with respect to Y, when D is 1, it's simply going to be minus of 1 over Y because the second term becomes 0. When D is 0, it becomes just 1 over 1 minus Y because the first term becomes 0. Right, and then again, let's look at some intuitions over here. I may run over a few minutes, guys, just bear with me, okay? Now, if the desired output is 1, and if Y is, do you want to increase Y or decrease Y? Increase Y, right? So what do you want the derivative to be? Negative or positive?
Negative.
Negative, right? Because you want to say that when I increase Y, the error goes down. What does this look like? Observe that minus 1 over Y is always going to be negative. But the desired output is 0. Do you want to increase Y or decrease Y?
Decrease.
So what do you want the sign of the derivative to be?
Positive.
Positive. Is it positive? Right? So you can just look at these derivatives and you can see that these behave properly. Right? Now, there's something very interesting over here. Now, when I plot this function, this is the KL divergence for the binary class. So the first picture is, now why the KL divergence? I could very well use the Euclidean, the L2 divergence even in the binary classification case. So why are we using the KL divergence and just not Y minus D squared? I could do that, right? So here's what. So here is the plot of the KL divergence when the desired output is 0. This is the Euclidean, this is the L2 loss shown by the red curve. The blue curve shows the KL divergence. Now, if it's not a cat, and if the network is 100% certain that it's a cat, how wrong is it? Is it just slightly wrong or infinitely wrong?
Infinitely.
Right? So also if it's a cat and it's 100% sure that it's not a cat, that's infinitely wrong, right? And so the KL divergence actually captures this very nice property that in the case of probabilities, being 100% certain of the wrong thing makes you infinitely wrong. And you have to change you have to move away from that solution really, really fast. But then this also has this very interesting thing. Let's say the desired output is 0 and the actual output is also 0, right? So If the desired output is 0 and the actual output is also 0, what is the slope? Is it 0? This is the desired output is 0 case. What is the slope? 1. When the desired output is 1, what is the slope?
-1.
Is the slope 0 at the correct answer?
No.
No. Is the error minimum at the correct answer?
Yes.
Right? So as you can see over here, although the error is minimum at the correct answer, the slope is not. And so what does this tell you? Is it sufficient to simply verify the slope? If you're doing gradient descent, can you just check the slope and say I'm not at the correct answer? You have to actually see if the actual error is changing, because when you're at the boundary of the feasible set, slopes need not be 0. That makes sense to everybody? Right. So this is for the 2-class case. So for a binary classifier, even though the divergence is 0 at the minimum, the slope is not. Something to note, right? For the multi-class case, this is just an extension of the same thing. Here, in the 2-class case, we just had 2 entries in the desired output. Implicitly, in the binary problem, the desired output was just either a 1 0 or a 0 1. In the multi-class, and so then correspondingly you had an output which is y 1 minus y, right? And so you multiplied this with the log of this guy, this with the log of this guy, and then you just added the whole thing up. In the multi-class classification case, this is just a generalization of the same thing. So in the multi-class classification case, you no longer have an implicit class. Every class is explicitly represented. And so you're going to have a desired output, which is a one-hot vector of some kind. And then you're going to have an actual output, which is a vector of probabilities. And then the KL divergence is going to be defined as the desired output times the log of the actual output for the class summed over all the classes. That makes sense, right? So it's simply, but then when you look at it, only one of these guys is 1, correct? These guys are 0. So what does this term end up becoming? Just the log of the probability, negative of the log of the probability assigned to the correct class. And observe that this becomes 0 when that becomes 1, right? So the KL divergence in this case is simply going to be minus summation, work through it is just minus log yc. Okay, but the more generic formulation over here, which is summation di log di minus summation di log yi, is also sometimes used when you use something called label smoothing, which you'll encounter in your class. But the simplest solution is just that the negative of the log of the probability assigned to the correct class is the loss. And minimizing this loss means you're maximizing the probability assigned to the correct class. Something crazy happens here. Is this guy a derivative, a function of the probabilities assigned to the non-target classes? No, right? So if I take a derivative of this loss with respect to the output of the network, how many non-zero elements will it have?
Just one.
Just one, right? Because it is not a function of the probabilities assigned to the non-target classes. So you're going to have, quite simply, the output, if my output is y1 through yn, n classes, my desired output is going to be a bunch of zeros and a 1 in one place. The loss is going to be simply the negative of the loss log of yi, which means the derivative of the loss with respect to y transpose, which is the gradient, is going to be zeros everywhere, because this is not a function of any of these terms. And for this one term, what's it going to be? Again, that's log of minus log y. What is the derivative of minus log y with respect to y? Minus 1 over yi, right? So again, the divergence is just going to be the have only one component which is not 0, which is minus 1 over y for that component. And interestingly, you will see that, again, this is always negative, which means you're always being told to increase y. Okay? So, great. And once again, you'll observe that this derivative is not 0 when the answer is correct. When the answer is correct, y is 1. The derivative slope is actually minus 1. So just looking at the derivative is not sufficient. So one final, give me a couple of minutes more. First, when you actually begin working with neural networks, you're not going to encounter the KL divergence. You're going to encounter cross entropy. Cross entropy, KL divergence is a sum of two terms. It's going to be summation di log di minus di log yi. That first term is not a function of y. You can get rid of it. Moreover, when the classes are represented as one-hot vectors, summation di log di simply becomes 0. So you're only left with the second term, and the second term is the cross entropy. So the two are strictly equivalent when you're using one-hot representations of classes, which is why we speak of cross entropy loss. And then there's something else that's very interesting. In that, when I'm computing the derivative of the divergence with respect to the parameters of the network, I can compute. So here is how it goes. I won't prove this, but the way you would do this, you have your network, and the network first computes an affine value z at the output layer, which is the vector, and then, this is z. You compute a softmax, and then you get a bunch of values y. And these are put through your cross entropy or KL divergence loss, and then you get a loss. We just saw what the derivative of the loss is with respect to y. But then if you compute the derivative of the loss with respect to z, which is the affine term that goes into the softmax, that it turns out is simply y minus d once again. And so the derivative of the loss with respect to the input to the softmax simply ends up being the error all over again, which is why we like to use the cross entropy loss in the case of classification networks. So both for L2, for regression and classification, if you use the L2 loss with the 1 over 2 factor for regression and the cross entropy loss for classification, the divergence of the loss with respect to the affine term before the final activation is simply going to be the error. For regression, the final activation is just an identity. For classification, it's a softmax, but the divergence is always just going to be the error. And this simplifies your arithmetic so much. You don't actually have to mess with working things out. So we've specified all terms over here. And in the next class, I'll skip the poll. We'll continue with how to compute stuff, how to compute derivatives in the next class. Thank you, everybody. Can you stop the recording? Just give me a second.